In this section, we're going to be focusing mostly on the graphs of trigonometric functions such as sine, cosine, and tangent, and the basic properties of such graphs when we say transform them and associated terminology. Also, I wanted to mention that there is some stuff in the packet and the slides that I'm going to skip for now, and we're going to come back to that in just a little in a later video. So in your packet, you might need to jump ahead a little bit. And we'll come back to that other stuff. But one thing that I wanted to mention about trigonometric functions is we often graph them with a slightly different looking xy graph than usual, which sometimes is called a trig window or a trigonometric graph. But this sort of window makes it a lot easier to graph points that we find from the unit circle of a trigonometric function. So for example, as we've been practicing evaluating, say, sine of pi over 3 or sine of pi over 4 or whatever, we know that if we're trying to evaluate sine of pi over 4, we need to figure out, well, what's the associated y value on the unit circle? And basically, in evaluating all those points, we can get a sense for how they work. And like usual, we could plot the points of a trigonometric function on such a window. So my point here is notice that the domain of this trigonometric graph is set from 0 to 2 pi. In that that's going to be one full circle on the unit circle. So what this graph will show is one complete period or cycle of the trigonometric function, where the y-axis is typically left unmarked, but you can pretend that it's 1, 2, 3, 4 as usual, or change it depending on the amplitude that you have. And we're going to get to that in a minute. But these sort of windows make it a lot easier to graph the trigonometric functions. We'll get to transformations in a minute, but I'm going to shift back to the packet and start working on that as I continue. So give me a second as I switch to my whiteboard. And let's start with sine and cosine. So I guess we'll do cosine first. And try to graph it just by the old-fashioned point plotting method. But the point of this video is to sort of comprehend why do trigonometric functions look the way they do, and then once we recognize their basic shape, we could apply that towards alternative examples with different periods. So let's start with cosine. And if we want to start with a graph, notice that I have a little t-table made with x and y being the cosine of x. But what we could do is start with those major quadrantal angles because those are definitely the easiest. So for example, if we wanted to know, well, what's the y-intercept of a graph of a cosine function, we could figure out, well, what's the cosine of 0 first. And to evaluate, we can always use our unit circle definitions that we discussed last week. So reviewing the cosine of an input is always going to give us the x value of that point, and sine is always going to give us the y value of that point based on t, the terminal distance from the initial point to the point on the unit circle. And another thing I wanted to mention, because this is a notoriously confusing idea, is that when we're using x and y, like the normal xy points on a graph, those are not going to be the same as the x and y's from the unit circle, because with a normal function, we're thinking about x is usually our independent input variable, and then we want to know, well, what's happening if I take the cosine of that value. But just to recall that cosine of 0 will return the x value on the unit circle, but this is not the same x. It's the x from the unit circle that we're going to get back. And notice with sine, it's still using x and sine of x, but we can just pretend it looked as it did before, like, well, what's the sine of 0? It would still return us the y point because that's what sine always does, regardless of these. So my final point here is the variables within this don't matter. It's a generic x variable, just like the x we use in a random equation. And that's definitely something that can be confusing in these sections, is there's so many different variables. But I think that's worth mentioning. Anyways, getting back to this example, if I want to know, well, what's the cosine of 0? So I'm just going to go ahead and write that there. I need to use the unit circle by the definitions that we talked about. Of course, you could use a calculator, but we're trying to do this all from understanding, a very conceptual-based approach, not just using a calculator to figure it out for us. But cosine of 0 should return, well, here's my input, which is the location of the point based on t. So 0 means it has not moved, or that would be at the initial point on the unit circle, so meaning we have not moved. And cosine always returns the x value at that point. So cosine, first I find my location, which is here, this point right there, and cosine will return x, which is 1. We could also fill in sine now, because as I said in the previous video, the x values are all the cosines, and the y values are all the sines. So what I'm going to be doing is referencing the unit circle to evaluate each of these, but the cosine of 0 makes 1, 1. Oops, that is not what I want either. Let me just undo that. Cosine of 0 is 1. And also noting that the sine of 0 is 0, because that's, what we're going to get to that in a minute. But those are two very fundamental points for what are the y-intercepts of those graphs. And also on our trigonometric graph, we could go ahead and graph that point as well. So essentially, cosine of 0 is going to make 1. Another thing I'm going to do with this particular graph is I'm going to put 1 right about here, just as an arbitrary choice. But it turns out that the max value that cosine can attain is 1. It can't get any larger, and so there is no point to making this 1, 2, 3, 4, because it actually will never be able to exceed 1. But at 0, cosine is 1, so that's our first point. Then let's graph some of these other points to try to determine what the shape will look like. So for example, if I want to do the next value, well, cosine of pi over 2 is just another random point. And notice that when I'm plugging in random values to try to determine what the graph looks like, it is more helpful to pick these sorts of values like pi over 2, because we know how to evaluate these based on the unit circle. Let's say I was trying to ask what's the cosine of 1. That's not something we're able to solve right now without a calculator. And well, actually, we're not going to get to that in this class. But it's notoriously confusing because there's all sorts of weird numbers going on. But the reason for these is they're just the ones that we can actually do. So if we go over to pi over 2, well, I need to know, well, what's the cosine of pi over 2? So I could go to the point, pi over 2 is here, cosine is the x, so that's just going to be 0. Cosine of pi over 2 is 0. Neat. And then we can continue. Well, the next one's going to be, well, what's the cosine of pi? And so on. Cosine of 3 pi over 2. So I'm picking those, what I referred to as quadrantal angles before, the ones that are on the axes, because those are kind of the key points on each graph of a trigonometric function. So at pi, cosine is -1. At 3 pi over 2, cosine is back to 0. And when I come back to 2 pi, cosine is back to 1. So kind of looking at that, basically I'm using each of these 4 key points to start and create my graph. Cosine of pi was -1, cosine of 3 pi over 2 was 0, and cosine of 2 pi was back to 1. And those are a lot of our important points. And graphing those on our trigonometric graph, so at pi over 2, cosine makes 0. At pi, and let's go ahead and make that one -1, cosine makes -1. 3 pi over 2 was back to 0, and at 2 pi, we got back to 1. And so the basic outline sort of appears to be a V, but this gives us the rough outline of the curve. Now, I'm sure you've seen the graphs of trigonometric functions before. They look, well, they're often what are referred to as wave functions because they have a graph not sharp or not a sharp V like this, but they're very curved, not exactly like a parabola, but sort of similar. They have a little bit more curvature to them. And to see a little bit more of that curvature more accurately, it will help to actually expand and graph more points in this, because these 5 points are good and all, but they're not really enough to fully see what it really looks like. And so another thing I wanted to mention is notice that those actually are the points that are labeled on a generic trigonometric graph typically, but also notice that there are more fine points in between those, which I wanted to mention, well, what are those? And if we really think about, well, what would each of these points be? Notice that from 0 to pi, we've gotten 1, 2, 3, 4, 5, 6 tick marks. And of course, right in the middle is pi over 2, because that makes sense. it's halfway to there. But notice that if we're thinking about what this one must be pi over 6 because it is 1/6 of the way. This one would be 2 pi over 6, which would be pi over 3. This would be 3 pi over 6, 4 pi over 6, 5 pi over 6, and of course 6 pi over 6. So basically it's counting in sixths, which is something you could remember. Now technically you could change that, but that's kind of how you can figure it out. And so anyways, I could go ahead and label this. This one's going to be pi over 6. This one's going to be pi over 3 because that was 2 pi over 6 reduced. The one after pi over 2 will be 4 pi over 6, which is 2 pi over 3, and then 5 pi over 6 before we come back to pi. But anyways, these are all specific points on the unit circle. That's another thing I wanted to kind of get back to is, well, if I wanted to figure out, well, what are the points for these tick marks? Those are also just on the unit circle. So for example, at pi over 6, we want to graph, well, what's the cosine of pi over 6? The cosine of pi over 6 is rad 3 over 2. And it's helpful to know, well, what is the square root of 3 over 2? Just for it will help us to graph the proper location, but that is approximately 0.87 or close to 0.9. It's going to be hard to graph exactly that value on such a graph, but it's kind of helpful to remember, well, what is that? Well, the cosine of pi over 6. Or additionally, if you make sure your calculator's in radian mode, we could just type it in, obviously, because our calculators are fully capable of evaluating trigonometric functions as well. But again, I'm trying to avoid relying on that because we don't really need it to do this. But anyways, at pi over 6 is going to be about 0.87. On the graph, well, if this is 1, this would be 0.5, so 0.8 would be somewhere in this vicinity. It's hard to be any more accurate than that. So I'm just going to put that point right there, which would be about 0.87. At pi over 3 then, another point on the unit circle, cosine of pi over 3 will return the x value, which is actually a little bit more easy because it's exactly 1/2 once we get to pi over 3. And at pi over 3, we got exactly 1/2. Neat. And also, if you want, there is one point on the unit circle that we skipped in this graph, which was the I believe my microphone turned itself off, so hopefully it is now working. But let's try to finish this graph before we wrap up this video. The halfway point is what I was just saying, which is a point that is not, you notice was not on that graph. But notice at exactly the halfway point, if we want to include every single one of these points on our graph, we can. But the cosine of pi over 4 is going to be right in between pi over 6 and pi over 3, halfway between 30 and 60 degrees, of course. But it will return the value of root 2 over 2, which is just another helpful value to remember the approximated decimal value of, which is about 0.7, pretty darn close. So anyways, if we do go to the halfway point and want to graph that, that's the midpoint between the initial and the top, which is about 0.7. So that would be somewhere along the lines of there, a little bit closer to 0.5 than it is to 1. But anyways, we can get a little bit of a better sense of what does the curvature of cosine actually look like if we connect the dots. But it has a nice continuous curvature to it, which is very different from the graphs of polynomials and exponentials. Kind of has some similarities, but it's a very unique shape to the trigonometric functions. And actually, when we get to sine's graph, what we'll see is it's actually exactly the same graph, and we'll see why it's very, very similar. But let's go ahead and finish it up, because that's just notice that if we're looking at this part of the graph, this is just the first quadrant of the unit circle, but we can continue going around, right? Because, well, we have, if I'm moving along these terminal points, cosine's returning x. But I could keep going and going and going and going to get the rest of the unit circle and complete my graph. But notice that as I'm going into quadrant 2, say I'm trying to do the cosine of 2 pi over 3 or 3 pi over 4, cosine is going to become negative and it's going to start going downward. Because at 2 pi over 3, cosine is now going to be negative 1/2. Then it's going to go to negative 0.7 and negative 0.87. So the pattern behind what's happening to cosine is actually going to continue to repeat itself. It's going to do the exact same thing over and over and over again because each of these points is symmetric. It's along a circle. So really we're going to observe that there is a very predictable pattern, which once we got those basic points, we can kind of figure out the rest of it from there. But cosine of 2 pi over 3 is going to be negative 1/2. I'm going to use red here just because I'm writing over my 2 pi over 3. And then it's going to go down to negative 0.7 in between and negative 0.8 at 5 pi over 6. And then it's going to go down to negative 1 as we previously marked. So in quadrant 2, as we trace along the points on the unit circle as we continue, it's going to go downward now, but have the exact same curvature. As we then move into quadrant 3, from pi to 3 pi over 2, we'll see that cosine is going to go to negative 3 root 3 over 2, negative root 2 over 2, negative 1/2, which is again those same numbers and in the opposite order, going backwards. So, and also notice that as we continue, this will be 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and finally 12 pi over 6 as we finish and get all the way to the end of the unit circle. But I'm not going to label those just because it's going to take too long, but this one will be 7 pi over 6, which is negative 0.86. Then in the middle is going to be 5 pi over 4, which is negative 0.7. Then 4 pi over 3. And then it's going to go down to 3 pi over 2 by the time we come back to the next x-intercept. Also notice that cosine has two x-intercepts, which similar to, not exactly similar to polynomials, the roots of trigonometric functions are quite an interesting field of study as well. And there's a lot of interesting math that connects a lot of the polynomial theorems we talked about, such as factorability, to trigonometric functions. And I don't want to get into that, but there's a lot of really interesting math that relates a lot of those ideas we talked about to the field of trigonometry. Anyways, then into the quadrant 4, we're going to now have 5 pi over 3, 7 pi over 4, and 11 pi over 6 as those 3 points, which would be 1/2 root 2 over 2, and root 3 over 2 again being 0.5, 0.7, and 0.87 as our next 3 points. So this one would be 5 pi over 3. This one would be 7 pi over 4, and finally 11 pi over 6 to trace each of those final points. And notice, if we're kind of looking at what's happening, we're sort of taking each of the points all along the unit circle, which if you count them all up, we got 1, 2, 3, 4, 8, 12, 16 total points, and we're just translating them, instead of being on a circular graph, to a rectangular graph. And that correlation is what generates this wave function. But what we can see is that that's often why trigonometric functions are called wave functions or circular functions. But notice the similarity, it's just a slightly different way of graphing it now, moving to a normal functional approach of graphing. But those values, you can kind of visualize it as tracing along the unit circle where cosine is the x. So if I think about, well, what's the distance to that point? We've got 1, because it's the full radius of the unit circle. Then as I'm moving, notice I'm getting closer and closer and closer and closer to that axis until I get down to 0. And basically that's being translated from a movement in the x direction to the wave going from 1 down to 0, because I'm moving in this way. Then I'm moving to the left, which would translate to downward. Then I'm coming back and forward. But as I'm tracing along a circle, paying attention to where x is exactly what the graph reflects. And lastly, in order to compare sine and cosine, one thing that I might refer back to later is just a little memory trick, is to remember the difference between sine and cosine is that cosine starts at 1, whereas sine starts at 0. From there, they're going to do exactly the same thing. And in the next video, let's do sine separately.